cloud. Okay, so we start the recording. So good morning to everybody. Today we have the pleasure to have with us virtually Maria Ubiali, that she's giving us a talk on can new physics be hidden in the proton PDFs. She's very expert in in collider physics. So please, Maria, go ahead.
Thank you very much. So it's a pity not to be there in person. I hope you will invite me again when it will be possible to travel. Anyway, so on this talk, I would like to look with you to explore this question which you have in front of your eyes: can new physics be hidden in the proton PDFs? It's a question that has not been very much explored so far, but I believe it's time to tackle it, and I hope I'll convince you that this is the case. So let me, of course, okay, so I will start with a quite broad introduction for those of you who are not expert on collider phenomenology and parton distribution functions. The first part will really be on what are these parton distribution functions, why they are so important, and why we use a lot of LHC data in order to constrain these functions. And this is presenting us with new challenges. And the second bit will be on the new frontiers, in particular, that have to do in general with the idea of wanting to look at all the parameters that characterize precision physics predictions, and in particular at the interplay between the parameters that determine the parton distribution function of the protons and those who determine this model-independent parameterization of new physics in effective field theories. And then I will tell you about a paper that we published recently where we look at this interplay in the deep inelastic scattering data that are really the backbone of our knowledge of the structure of the proton. And then on a new project that I'm working on with my PhD student and a few external collaborators. So as I said, feel free to interrupt me at any time if you have questions, or if I say something you don't agree with, or if I just say words and taking for granted that everybody knows what I'm talking about. Okay, so this is a plot that you might have seen many times, but I always find it impressive to see, it's one of the Atlas standard model summary plots, to see the range of measurement of observables, so in terms of cross-section, and the impressive agreement that we have between the standard model predictions, which are the prediction you see there in gray, and the measurements at the 7, 8 TeV and 13 TeV, so the measurements that are done at the Large Hadron Collider. So on the one hand, this plot is telling us that for many observables, the experiments at the LHC are doing better than the theorists. So especially for those of us who work in precision phenomenology, we are really challenged to go beyond the state of the art of our prediction. In particular, things that before we could not care about, now we have to worry about. And I will give you some example later. And the second message that I get from here is that clearly, if there is, as we hope, as it must be, physics beyond the standard model, it's probably gonna show as like small effects from the standard model predictions. There are different scenarios in this hunt for new physics that the Large Hadron Collider community is doing. So in particular, if the scale of new physics, which I indicate by lambda here, is within the reach of the Large Hadron Collider, so a few TeV, of the order of the electron scale, we would see some bump in some distribution probably. And a bump is a bump, so we don't need much precision physics to find it, but we clearly need precision physics in order to characterize it and to disentangle from the standard model background. But if new physics is beyond the scale that can be reached at the LHC, at that point, one of the most likely scenarios that there will be like subtle deviation from the standard model across a wide range of predictions. So, and it's essential to have some precise and robust tool in order to spot all the subtle deviations. Okay, so this is the kind of the aim of, the way I see what is the aim of the current hunt for new physics at the LHC. So when I talk about standard model theoretical prediction, what do I mean? So, sorry, I need to move this. Okay, so we have several ingredients that enter precision, precise theoretical physics prediction, like in particular, whenever we look at the proton-proton collision, if we look at the Parton level cross-section, we need to know really well from the theoretical point of view 2 ingredients. So what I circled here in blue, that is the hard scattering cross-section, and this is something, the partonic process, and that's something that we know by using perturbation theory, and including more and more QCD correction and electroweak correction to the hard process over there. And in that, there has been an enormous progress in achieving higher perturbative order in the QCD prediction, incorporating together with electroweak corrections and do automated calculations of that. And the other ingredient that is essential is the one that is circled in pink, which are what are called Parton distribution functions, which are the function that parameterize the structure of the proton in terms of its elementary components, that are the quarks and the gluons. These are functions that cannot be determined by means of perturbative QCD. Rather, we extract them from experimental data. And this can be done because of 2 things. So first of all, they are universal. So these Parton distribution functions do not depend on what is the hard scattering process that you have here circled in blue. And second, because their dependence on the scale at which the process happens is something that is predicted by perturbative QCD. So what we really need to extract from the data is their dependence on X, which in the leading order picture in the Feynman-Parton model, we can imagine as the fraction of the momentum carried by one of the elementary components of the proton. So how do we extract these functions, their dependence on X, from the data? And how do we extract this delta I, so their uncertainty? So this uncertainty at the moment is something that if we had an infinite amount of data from which we wanted to extract these functions and they were all perfectly compatible, would go to 0. But clearly this is not the case because we live in a real world and not ideal world. But let me say just in a nutshell, what are the ingredients that we need in order to extract functions from the data. So first of all, we need a lot of experimental data. I will show you later on what are the typical data that are used in order to extract these functions. Then we need, of course, theory calculation, because you see in this, okay, I don't know how to point things, but okay, you see here in this blue box, so you have the 2, so the Parton distribution for proton number 1, proton number 2, they're convoluted with the partonic cross-section, so the hard scattering, and then you get sigma, which is what is measured, and so we need the sigma hat. We need the partonic cross-section, which are calculated using theory in order to extract this function F1 and F2 from sigma. So this is, again, we need perturbative calculation, fast interfaces. We need to deal with details that are very important, like the way in which we treat heavy quarks, the way in which we include electroweak correction in the theoretical prediction. And then, of course, we need the whole statistical thing, so the whole methodology. So we need to parameterize the functions that parameterize the proton. We need to have a way to propagate the uncertainty of the data into this delta I, which is the uncertainty of the function. And we need to have a good, solid fitting methodology. Then you mix all these things up together and you have your nice PDFs, which you can see here. So typically these Parton distribution functions, they are parameterized at the hadronic scale, so a scale that is about the mass of the proton. And as you can see now here, doing this whole fit that I just gave you the main ingredients, we determine, you know, the PDF of the gluon, the up quark, the down quark, strange, and so on and so forth at a kind of hadronic scale, and then we evolve using this renormalization group equation, this DIGLAP equation, to any scale. And these functions and their uncertainty become the input of a theoretical prediction. In particular, so before going into details, let me show you why these functions, so the uncertainty that we have on this right-hand side plot is important, because at the moment, in this precision era, as I was telling you, so where the hard scattering cross-section is known to higher and higher perturbative orders, is essential to have control on this uncertainty on the PDFs. So for example, Higgs physics, which is one of the portals to physics beyond the standard model, where we can, it's a kind of the least known sector of the standard model where we can hope to spot deviations. So if you look here at what's the percentage theoretical uncertainty coming from these two ingredients, which I circled below as the uncertainty of the hard cross-section and the uncertainty on the PDFs, you can see that, for example, for gluon-gluon fusion, the uncertainty, so the blue, which is the one for the PDFs, and alpha S, and red, that is the uncertainty associated with the hard scattering cross-section, the fact that we do not know the missing higher orders, these are compatible, so of the same order of magnitude. When we look at vector boson fusion, which is the second highest, most likely way in which the Higgs can be produced, the PDF uncertainty dominates, and so on and so forth. So clearly, this uncertainty on the function, on the PDFs, is a limiting factor in the accuracy of theoretical prediction. So we want to bring it down in order to have more and more precise standard model predictions. Again, another reason, if you look at one of these recent Atlas and CMS paper on the determination of the standard model parameters doing this global fit on several observables. For example, the determination of the W mass from Atlas, you can see that in the table below here, you have several uncertainties, and the dominating one in the extraction of MW from Atlas, which is this red thing you see here, is dominated clearly by the PDF uncertainty. Again, if we see a bump in the distribution at some high invariant mass, okay, which we know that the PDFs for large X, which is when the partons carry a large fraction of the momentum of the proton, are really badly known because there are few data that constrain them. So for example, here, this is the cross-section for the production of gluino pair of a mass that goes between 1 TeV and 2 TeV. And you can see that in this case, the uncertainty, this PDF uncertainty is of order 50 to 100%. So clearly, if one wants to characterize new physics, one has to bring down the uncertainty in the large X region of the PDFs. And then there is a subtle point, which I think is very important. So, which I think has to do with what I'm going to say later. No? So for example, this is something that happened in 1995, so more than 20 years ago. So at the time, the PDFs were not determined in a fancy way as we do now. So there were only some central values determined by different groups, and there was not an uncertainty associated with the PDF. And at some point, there was this apparent discrepancy between the standard model calculation and the CDF jet data. And you can see that this discrepancy was in what it was the high invariant, in the high energy region. But again, because there were no robust uncertainty, people thought, maybe here there is new physics. But then CTEC, which was one of the collaboration that was making the fits at the time, they included this data into the fit of the PDFs, and suddenly the discrepancy was completely reabsorbed. So I think this is something that we have to learn from, because I always presented this slide as the message: we really need to have a robust determination of the PDF uncertainty. Now the question that I have is, what if we do the same thing now? So we keep adding new data. So we see a discrepancy, then you add this data into a PDF fit and suddenly it goes away. So we have to make sure that the uncertainty we have in the PDF is robust, so that if something is outside the prediction, it's not due to the PDFs. And that's, we are kind of far from it still, I think. Okay. So I hope that this gave you an idea of what I want to talk about. Let me give you a few more details on the PDF fits, which are relevant for the question that is the center of my seminar. So as you can see here, this is the kinematic coverage in the leading order kinematic. So here is the X that each data constrain, and on the y-axis you have the Q square, so the scale square that is constrained by each of these data. And you can see there are different colors. So like in orange, there are the deep inelastic scattering data from the old fixed target experiment and from HERA, so the electron proton collider that stopped running a few years ago. Then there are a lot of data that are here, which already are at high energy, like the data from Tevatron and the data from LHC. In particular, at the moment, we include a lot of jet production data, Drell-Yan invariant mass data, top per production data, and so on and so forth. And all the PDF collaborations, including the NNPDF collaboration, which I started 15 years ago, we include more and more data that come from the LHC. Clearly, the data do not measure a PDF. They measure a combination of different PDFs constrained at in different X regions, and each data constrains some, so has more power to constrain some combination of PDFs. No? For example, the jet data constrain a lot the gluon, or the HERA data constrain very well the valence, up and down PDFs, and so on and so forth. But as you can see, a typical modern fit of PDFs include more than 4,000 data points. So it seems like a simple problem, because you have parameter, you have data, you do a fit, you determine it, but clearly there are always some, it's not as easy as it seems, because we have a finite number of experimental data and we want to determine a set of function with the error. So somehow we want to determine an infinite dimensional object, this probability in the space of PDFs, from a finite number of information. So you have to do some trick in order to do that. So the kind of traditional determination of PDFs rely on choosing functional forms for the up PDF, the down PDF, U bar, D bar. So typically 7 functions are parameterized because they have the quirks. They usually are generated perturbatively. And once you decide what is the parameterization, then this infinite dimensional problem is projected into the n-dimensional space of parameters. And then people look at the chi-square to the data in this n-dimensional space, and they find the minimum using the Hessian methodology, and adding a tolerance, so a delta chi-square that determines the uncertainty of the parameters, okay? And the typical parameterization, there are about 20 to 40 free parameters for 7 independent functions, so there is always some normalization, x to the a, 1 minus x to the b, and some polynomial. So that's a kind of traditional approach. In 2008, with the NNPDF, we decided to use a different approach. So instead of using a Hessian method to propagate the uncertainty of the data into the uncertainty of the PDF space, we decided to do a Monte Carlo sampling. So basically, we generate a sample of the experimental data, so like whatever, 100 or 1,000 pseudo data that are distributed according to the experimental data distribution. So they have the same correlation as the experimental data that we want to fit, the same uncertainty, and so on and so forth. And then for each of these copies of the data, for each of the pseudo data, we fit the parameterization of the PDFs. In our case, we didn't want to have a bias related to the fact of choosing a particular functional form. So we used neural networks that at the time they were not so fancy as they are now. But anyway, for us at the beginning was a way to have a flexible parameterization that had many more parameters that would not introduce any bias. Clearly, when you do that, you have to be careful with the minimization, with stopping the algorithms, because if you have a very big parameterization of function, you always risk to overfit the data. But as you can see, for example, our gluon PDF, that was a long time ago, now it has changed, but the spirit is the same. So each of the green lines you see in this plot on the left-hand side is the best fit for a replica of the data. And as you can see, they have widely different functional forms because the neural network parameterization of each of the flavor gives you different answer each time you minimize. And then, you know, once you have all these green function, which are the replica, this has built an ensemble in the space of the PDFs. So the central value is taken as the average over these 100 green values, and the same way you can take 68% confidence level, 95%, 1 sigma, whatever you want. No? So then you have really a statistical distribution of the PDF. So it's a Monte Carlo sampling of the probability space into the PDF space. Okay, so that's really in a nutshell of what we do. Okay, as I was saying, the way, so the gluon, from what you can see here now that had a very wild uncertainty, has improved a lot. So we have reduced the uncertainty of the gluon because we have added many, many data, in particular the data from the LHC. So I would say that in the past 5 years, the LHC data into a PDF fit are becoming increasingly important, and they have reduced the uncertainty of the PDFs, which is what we want in order to have precise phenomenology. So for example, this is the latest set, which is NNPDF 3.1, which includes a lot of LHC data. You can see that the uncertainty of the gluon has decreased quite a lot, and also the uncertainty of the light flavor. So LHC data really provide a powerful auxiliary and new constraints on the PDFs. And it's very interesting, you know, also from the point of view of testing QCD, that processes that are very different, so also the theoretical prediction are different, and also the kinematic range that they cover are different. So inclusive jet or top pair production or the transverse momentum distribution of the Z boson that are all initiated by gluon PDFs. So they're very much dominated by the gluon. It's very interesting that they can all be fitted together, and that including all these processes that constrain the gluon in different regions, we can have a very sensible reduction of the gluon uncertainty. So the red line, the red dotted line that you see was the gluon uncertainty in this X region between 10 to the minus 4 and 10 to the minus 4 before including this data. And after including all this data at the same time, you see that the uncertainty is reduced by a factor of 2 in some regions. So that's a very nice test of standard model, if you want. Okay, so now let me say something. So that's a problem that we never had now. So we have refined our tools. So we have a nice methodology, but and we want to reduce the uncertainty on the PDFs. And we somehow have succeeded to do so in a sense, because this is now the PDF uncertainty in the production of a particle with a certain mass and at a certain rapidity. And as you can see here, for different luminosity challenge, either quark, 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 gluon, 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 you can see that here they're different. You see that so if you compare the left to the right-hand side plot, thanks to the inclusion of all these LHC data, we have a 1% accuracy, so an error only 1% coming from the PDFs, which is great. On the other hand, we ask ourselves, now that we got there, can we really trust this 1% accuracy? Because we are talking of a small number. And if, so people have looked at the projection of what will be the PDF uncertainty and theoretical prediction in the high luminosity era, and this, you know, depending on the scenario, but it will go down to like 0.5%, no? So even smaller. So at that point, one has to be really careful, no, on the product you give, because, you know, we definitely get precise PDFs, but the point is, are these PDFs also accurate? So do they really do they really get the center of the target we want or not? Because we have seen in the past that very often when people publish an updated PDF set, so a new fit, where new data have been included, things have been refined, sometimes you get PDFs that shift with respect to the previous PDF by an amount that is larger than the PDF uncertainty that we associated with, okay? And this is something that we have to answer, you know, why did this happen? Because somehow if you give a PDF that is perfect, somehow you should account for new data that you include, no? So clearly there can be many reasons, and this is something that we have to be more and more careful in disentangle which one is the reason why sometimes when a new PDF set is given, the new PDF is outside the error band of the previous one. It can be because the data are inconsistent with the ones that were included previously. Is there a tension in the data? Or, so I try to give some example. For example, for the strange PDF, there has been so far a lot of observation that somehow the data in the fixed target, so for example, the old NUTAP data tend to suppress the strangeness content of the proton, while the LHC data tend to enhance it. So somehow there is a tension between the two. So there seems to be a tension between the two. And this clearly, if one doesn't have a flexible enough parameterization of the strange, you don't manage to get both, to reconcile both data. Or sometimes the problem is in parameterization that, for example, simply because new data are added, if you have a fixed parameterization, sometimes you have to add new parameters. And this changes the shape of the PDF. It has anything to do with the physics. It doesn't have anything to do with the information that the new data take. It has to do with the lack of flexibility that the parameterization had before. So for example, the CMS-W asymmetry data, when they were included in the MSCW parameterization, they had to change and add parameters to the U valence and D valence, otherwise they couldn't fit this data. So the difference that you see between this pink error band and the red, it's not a tension in the physics or in the PDF, is the fact that the parameterization was updated a posteriori. Or sometimes the whole thing we can see are due to the fact that the methodology has been improved. So the whole fitting machinery has been improved. Like, for example, even in the NNPDF collaboration, when we move from 2.3 to 3.0, the shift due to the change in the minimization was at the level of 1 sigma. Okay, so that's why from now we and most of the PDF collaboration, so we do disclosure test in order to make sure that we get a robust statistical interpretation of the uncertainty. But this, the shift that we can see can also be due to theoretical framework. So for example, this is a paper I don't have time to talk about, but theoretical uncertainties that were never included in the fit of PDFs. So somehow the theoretical prediction we had for all the observables that we included in the fit were taken as true. So the fact that they also had a missing higher order uncertainty was not kept into account, because we could ignore it so far, but now we cannot do it anymore. So we started to look into that. And the other thing that I think is interesting to look into is the BSM effect. So we always assume that PDFs, so that the processes that we fit are well described by the standard model theory. So that's the next part of my talk. If you have any question concerning the first, I can stop. If not, we can keep for the end of the talk.
Yes, I have one question. So you have been able to constrain quite highly the large X region, but then it seems that not much in the small X region in the last few years. Is that true?
Yeah, a bit in a sense. The problem is that in the small X region, we have a lot of constraints by HERA, so the HERA data. And now we have also some measurements from LHCb that have helped in reducing the uncertainty in the small X region. But yes, there are processes that can be included. The problem in the small X region is that when you go below 10 to the minus 4, 10 to the there are some effects that go beyond the QCD factorization that we use. So in a sense, there are small X resummation that need to be included, or effects of saturation. So things that are not accounted for.
But in principle, when you use this neural network approach, how much of this collinear factorization or KT factorization do you have in your assumptions for the functions? Or you don't, because I understood you have nothing. So
no, we do have. So in a sense, we have nothing in terms of the parameterization of PDFs, but the theoretical framework is the collinear factorization. So everything we do is, sorry, I didn't, it's here. It has this, so our fit is based entirely on the collinear factorization.
Okay, that's the limitation when you go to the small X region. I see. Okay.
Exactly. So, that's why, in a sense of theoretical uncertainty, we have to account for the fact that the collinear factorization has an uncertainty itself. No? So, as you say, in the small X region is not accurate.
Yeah, in some sense, these measurements with a very forward Drell-Jan per production at the LHC could be something to add and to see what is going on there. Yes, that's interesting. Thanks.
Exactly. But we need to have a framework in which to include this small X and see what's the difference. No? Because otherwise we have a bad chi-square, a bad agreement with the data. We don't understand where it comes from.
Yes. Thank you.
Okay, so very good. Let me move to the last part of my talk. So so this is something I took from a talk here. Sorry. So clearly, very often the new physics effect look at the tail of the distribution. So the high invariant mass distribution. And always the question is, if you see something that is higher or lower than the standard model prediction, is it due to new physics or a limit in the understanding of the proton structure? So that's a question that comes up very, many times when you give a talk of PDFs, which is a question somehow that the historical digression that I did before, somehow it's something that can be applied now to this region, which is something that we don't know really well. Before trying to answer in this question, let me just say the context in which I want to do this investigation. So the context that we looked in so far is the standard model effective field theory, FITS. So that's a useful way to look for the effect of new physics in a model-independent framework, is really to use this EFT approach. So the idea is that the scale of new physics probed at the LHC is much higher than the scale at the LHC. And basically it can be integrating out the new degrees of freedom that live much far above the LHC scale and add higher dimensional operators to the standard model Lagrangian. In particular, SMEFT is low energy limit of a UV complete theory that has the standard model, that assume the standard model field content and symmetry apart from the accidental symmetries. So there have been a lot of work in the SMEFT, there are a lot of fits looking at different observables. Clearly they always limit the analysis to a finite subset of operators, because in a sense, even only considering dimension 6 operators, there is a huge number of operators, like 2,500 operators without any flavor assumption, that is reduced when flavor assumptions are made. Okay, but the good thing is that it's a fully renormalizable, fully fledged QFT, so one can compute this prediction, in a sense one can do precise SMEFT prediction, including higher orders in QCD and electroweak. And also it can be matched to any UV theory that reduces to the standard model at low energy. Okay, so let's go back 1 second to see what people do when they do the SMEFT fits and when they do PDF fits. No? So usually the collinear factorization is always assumed, even implicitly in all of this fit. So you have the proton-proton cross-section that is measured at the LHC. This is compared with a theoretical prediction, and from that some parameters are extracted. No? So when we do the fit of the PDFs, comparing the theoretical prediction to the measurement, one extracts the parameters of the PDFs. In the SMEFT fit, what one does is that you have your Lagrangia, that is the standard model Lagrangia, plus these higher dimensional operators with these Wilson coefficients in front of dimension 6 and dimension 8 operators, and comparing the measurement to the theoretical prediction, one extracts the limit on these C coefficients, on the Wilson coefficient that are there in the expansion of these higher dimensional operators. And so this is the plot that I showed you before, no? The kinematic coverage of the data that are used to extract the PDFs. As you can see, these data are used in both words. So they're used to extract the parameters of the PDFs, because the top data give a strong handle on the gluon, but they're also used to determine the Wilson coefficients of the operators that are relevant for the top. No? So this is a reference to one of the recent analysis where I think 34 operators are fitted at the same time in the top sector. It's exactly the same data. Or the same, for example, for the jet data. So they are an important ingredient in the PDF fits that we use to constrain, especially the gluon at large X, but they're also used in order to determine some of these Wilson coefficients in JET's dedicated analysis, like as you can see in the paper that I cite here. And the same, for example, for high mass Drellian data. So there is, again, very often, I couldn't cite the whole literature because it's huge, these tails of the Drellian distribution are used very much in order to extract information on contact operator, like 4 fermion operators. And these data are also used to determine the PDFs. So what do we do? So because at some points, somehow the trend is to keep including higher and higher energy data. So either we say we stop because we don't want to fit somehow the effects that might be there due to new physics that appears in the tails. So we somehow put a cuts into this plan, you know, so we say, okay, we use the data only below a certain Q square or that has some, and stop including the higher energy data. Or we study a way in which we can have conservative PARTON, so meaning that we can make sure that all the observable that we include in a PDF fits are really described well by the standard model, so that any tension that we don't understand in the data, we throw away the data. Okay, so that's a direction that has been mentioned many times, but there have never been studies on, you know, what is the Q squared at which we stop including LHC data in the fit and so on, or how we determine which data to include. So that's clearly something to be investigated, and that no one has done this so far in a kind of systematic way. Or another thing that one could do is to really do a simultaneous determination of this data, meaning that of these parameters, you know, because in the end, they all, so when you include some LHC data, they depend both on the parameters of the PDF and on the Wilson coefficients that you add for the expansion of the observable. So that's something that I wanted to look into, because a simultaneous determination really helps us in understanding the interplay. What do I mean by that? So from the PDF point of view, the question for me is, how do we make sure that we do not fit away new physics effects into our fits of the proton structure? So bending the PDF so that these effects can be absorbed. And from the SMEFT point of view, somehow all the bounds on the SMEFT operators are determined by assuming that the PDF that we include are standard model-like. So instead, how would the bounds change if I was using PDFs that include the effect of the operators that I'm fitting? So if these effects are also included in the fit of the PDFs. Let me do a quick digression that seems to be unrelated, but actually it is. No? So for example, PDFs and alpha S. No? So the Parton distribution function of the proton and the running of the strong coupling constant, they are very much correlated, because clearly the PDF evolve with the scale according to the Diglap evolution equation. So their evolution is determined by alpha S. And also because, you know, this the way they are determined. So you compare the perturbative expansion of the hard cross-section to the measurement, and you determine the PDFs. And this is one of the latest plots from the PDG, I think 2020. And there are many determinations of alpha S. And the cleanest one are the ones that do not require any knowledge of the PDFs, if you want. However, there are also, as you can see here from the various determinations of alpha S that rely on the measurement of proton-proton processes, and some that come from the determination of alpha S in a PDF analysis. So clearly, in a sense, it's less clean, but it has the advantage that is driven by the combination of many experimental measurements. So what it was done, so because they're very much correlated, so this is one of the fits that we did, I think 5 to 7 years ago. No? So you can do a fit of PDFs by setting alpha S to a particular value. So the whole fit of PDF is done by setting alpha S of the mass of the Z to whatever, 109, 113, 150. So you do a scan along this single parameter, and then one looks at the minimum of the chi-square to the data as you use a different value of alpha S, okay? So it's changed both in the PDF and in the parabola. So this is what we did. Recently, we managed to do a simultaneous determination. So it was not you fix, you fix the value of the alpha S parameter, you do a fit, you measure the chi-square, you put a point in the parabola, but really to build these replicas, which I was showing you before, by doing a correlated replica sample. So changing alpha S and the data at the same time. So in this way, as you can see, so so somehow the uncertainty on alpha S, because it's correlated to this sigma hat, which are the parameter of the PDF, would be the real uncertainty. So it would really be the intercept of this ellipsoid along the y-axis, while before we were always projecting on to what we call sigma old, because somehow we were only looking at the minimum of this parabola, keeping it fixed, so without varying it at the same time. So that's something interesting, because as you can see, I could say alpha S of SMEFT or SMEFT operator, and somehow the substance doesn't change, although they are much less correlated if you want. But sometimes alpha S is determined by looking at the specific LHC process. So a process involving proton-proton, you look at the chi-square to that process, and then you determine alpha S. There was this paper recently that said, so here I just reported the abstract, that basically any determination of the strong coupling constant alpha S from a process that depends on partonic, sorry, I can't read because I have my screen, of partonic distributions such as hadronic processes or deep density scattering, doesn't lead to a correct fit of alpha S unless it's determined together with the PDFs. So this paper I think is very interesting, because it showed that for things that are so much correlated, like the PDFs and alpha S, you cannot determine the one without the other. Because what you get as a result for alpha S is very different from the one that you get when you fit the data along with the PDFs. So for example, if you only focus on the ZPT observable, you get alpha S at the mass of the Z that is 0.124. If you instead do the whole fit of PDF plus alpha S, you get alpha S at the mass of the Z of 1.185. So these are very different answers. And if you think about this, could happen also for the SMEFT coefficients. So I think it will happen in a much less strong way, because as I said, the correlation is different, but nobody has ever explored the correlation between these two. So if I still have, oh sorry, I'm very late. Okay, I will go quickly, just I show you what we did to answer this question, to try to do a simultaneous fix. So we said, let's only take the DIS data, which are really the backbone of the determination of any Parton distribution function set. And as you can see, they do not go very high in Q square, but they get to Q square, which is about, where is it, 5 10 to the 4 GeV squared. So, and what we did here, we said, okay, let's include in our theoretical prediction, so the prediction for the hard partonic cross-section, not only the standard model operator, but also the 4 fermion operators, in particular between two right, with right helicity. So just because we wanted to start with a small basis with only 4 operators, okay? So we choose this subset of the Warsaw basis, which is lepton universal. So we can take L, so the lepton can be either an electron or a muon, and then we split the flavors. So the operators are sensitive on whether we have it up, down, charm, or strange quarks. So what we did is that, okay, let's compute the dimension 6 operator and dimension 8 that enter a DIS cross-section. And let's see how our theoretical prediction would change when we include a non-zero coefficient for these 4 operators that I mentioned. So, and indeed, you know, even looking at some in the region that are still allowed by LEP and by the LHC data that have been analyzed so far, you can see that especially for the electron-proton collision at Hera, there are corrections in the high Q square region, about 8 × 10⁴, that are between -10 and -20%. You know, so the ball is not negligible, and these data are very precise. So they have an uncertainty about 5% in that region. So we try to see, first of all, sorry, I don't have time to go into details because otherwise I would speak too much. But so what we did is that we looked, so we did something like a scan over the parameter space and look at the chi-square to the data as a function of the parameters. And we found these individual and these marginalized bounds for these Wilson coefficients, where in this case lambda is equal to 1 TeV. Okay, could be rescaled. But then okay, these are bounds that everybody could compute, not doing the standard SMEFT analysis. So there is nothing that has to do with PDFs at this moment. And what we did, so these are really the confidence intervals on this Wilson coefficient using the DIS data. So what we did next is, okay, now we allow the PDFs to change in the presence of the SMEFT operator. So instead of using standard model PDFs for each of these benchmark point that we were scanning, we were using PDFs that were fitted by turning on that particular Wilson coefficient. So it's like moving across the parabola of alpha S. So we employed the NNPDF methodology to fit this PDF from scratch using this SMEFT modified theory. And we see what happened. So, so first of all, how is the description of the data? So the answer is that for a few benchmark points, the description improves. So there is a delta chi-square equal to -20, and for many, the description deteriorates, okay? And clearly the Hera data dominate this whole analysis. And how do PDF change? No? So when we feed the PDFs, assuming that, you know, if there is new physics, it does affect also the observables that we fit there, we can see that somehow the gluon, that is the one that changes the most, is still within the uncertainty. So it doesn't change in a way that completely screws up the PDF fits. And in some region, it's a bit, so it's within the 1 sigma uncertainty, but you see that it's not equivalent to the one we had before. So, sorry, let me skip that. So let me just partially answer this question. So can new physics absorb, so can PDFs absorb new physics? So in this analysis, we can say that the PDF, so the answer is that they can only partially do so, because in a sense that we can see that there is a distortion in the PDFs for some benchmark point, but this also leads to a significantly worse description of the data. And indeed, we verified that somehow increasing the cut on the Q of the data causes a deterioration of the agreement to the data. So somehow this tells us that if we add new physics into the theory for the PDF, we have a worse description of the data. And how do bounds change if the PDFs are fitted along with the dimension 6 operators? And as you can see now, for example, for the individual bounds on the AU coefficient or AD, we can see that the consistent inclusion of this effect into the PDF fit slightly increases the size of the contour for this, but not dramatically. So they're not shifted dramatically as it was in the case of alpha S. So if we look at the marginalized bounds, they are still compatible with each other, but I would say that if one does this simultaneous determination, they do actually increase a bit. So somehow there is more room for new physics if you do that. Okay, so given that we are not satisfied, in a sense, these partial answers are on the one hand reassuring, because if the DIS data were not safe for BSM physics, we would be screwed up. We wouldn't know how to determine PDFs from. But on the other hand, now we say, okay, what if we really do the same analysis by including higher invariant mass data? So really the Drellian data, the tails of the Drellian data that are used both in the PDF analysis and in this SMEFT analysis. So this is an analysis that we are doing with the collaborator that I showed you before and with my PhD students, and stay tuned for results. So clearly the effect is bigger. So we can see that now we need to quantify it, and I hope we will publish a paper soon, and maybe I can come next year to present it to you. And also, but I think this is what I'm most excited with, is really to have a solid methodology in order to really do simultaneous fits. So, which is, you know, somehow so far what we did was fine for up to 4 to 6 Wilson coefficients, but what I want to do is to really have a big basis of Wilson coefficients and be able to determine simultaneously the SMEFT coefficients along the PDFs and other parameters that enter the PDF determination, as you can say alpha S or the sign of theta Weinberg and so on and so forth. And these are preliminary results. So I ran our methodology yesterday just to show you the plot. So this is, for example, the simultaneous determination of the gluon. So this is the orange is the new gluon, and this is fitted at the same time as these 4 Wilson coefficients. But in principle, one could do it with up to 100 or even more Wilson coefficients if it's solid enough, but work in progress. Okay, sorry, it's 4. So let me just say that I think that precision physics opens up new fascinating challenges. I showed you how it's important to have a very sound and robust determination of the PDFs, and what are the challenges we have in front of this accuracy versus precision frontier. And I hope I convinced you that it's time to study the interplay between new physics and PDFs. So the way forward is really to look at really the data that have high mass, so that they can really have these effects and see how, you know, whether the answer that we got for DIS still holds or if it's modified. And the ultimate goal is really to have the simultaneous fit of Wilson coefficients and PDFs. Thank you for your attention.
Thanks a lot to you, Maria. I hope you can see the people clapping. Thank you. Thanks a lot for the interesting talk. Is there any question, comment from the others?
Hello?
Yes.
Hello, my name is Maria Jose Herrero, and I am curious about one thing. Are you listening to me?
Yes, yes. I don't see you, but...
Yes. Don't worry, don't worry. No, my question is related to the Wilson coefficients, to the last part of your talk. I wonder if it would be more realistic if you include the Q-square dependence on the Wilson coefficients themselves, because as you know, these evolve also via the renormalization group equations, and my intuition is that a really complete point of view in this approach, which I find very interesting, would be to include also the Q-square dependence of the Wilson coefficients. As you know, it's like the case of alpha strong. You include the Q-square evolution of alpha strong, and you see if you put all together alpha strong and PDFs, how the fits change. But in this case, it could be very relevant, that dependence, in my opinion. What do you think?
You're right, absolutely, because it's something that for them, if you look now at this DIS analysis, we didn't do because somehow the Q square was only up. If you look in terms of Q, was only up to 230 GV, so it was not really high. So the running of the operators was of the Wilson coefficients was not very relevant, but for Drell-Yan, in which we will go up to, where is it here? So these are the data points that we are including in our analysis. I didn't have time to discuss much them, but as you can see, they go up to 2 to 3 TeV. At that point is what your point is absolutely relevant. So that's what we are including now. So we haven't implemented it yet, but this is something that we will definitely implement in this analysis. Because as you say, as for the strong coupling constant, the same applies for the Wilson coefficients, yeah. Okay, and it mixes up operators, so it's a bit more complicated.
Okay, thank you very much, Maria.
Thank you.
Any other question or comment?
Yes, I have a question.
Hi,
Sven. Hi. Thanks for the nice talk. You were mentioning the determination of alpha S and corresponding PDFs from a subset of processes, and you showed how one can be off by not taking into account also the PDF determination at the same time. Now, there are several groups in the world that do PDF determination and alpha S determination. And if I remember correctly, there was always one group that kind of deviates from the others. They use, I think they use mostly HERA data. Is this maybe related to what you were saying, or what this new paper that you were mentioning analyzed? Or, I mean, if there are large deviations between different groups, what does this tell us then about the reliability of the PDFs that you were stressing so much?
Yeah, absolutely. So that's a very important point. So I think, so the ABM group that you are referring to, so there are several differences that were discussed in, so one thing that is crucial, and it's something that it would be really worth exploring, is the parameterization, because somehow, as I was saying, if you have a fixed functional form, like for example, they only use one parameter for the gluon at large X. And I think this, because the gluon is so much tied up with alpha S, so there is such a strong correlation. I would like to see, whether the different results, for example, that are obtained is due to this fact that the parameterization is too restricted, and therefore somehow you don't have much room to move around the space when you do the simultaneous determination, or it's due because maybe the data, or maybe, they're right, but they always stress the fact that you have to determine alpha S and PDFs at the same time. So I think this is right. This is something that you have to say that. But I think that because of, so I think they should update a bit the parameterization, because otherwise, it's the right concept, but perhaps you don't get the right answer because of some tensions that you don't reproduce.
Okay, thanks a lot.
Thanks, Ben. Other questions or comments? I have also a question. So you said that you are using the standard model FET theory to make part of the fit. What if you use a more generic FET theory, like the X-FET theory, where essentially the X is not taken as a doublet, but is more generic object? Does it affect your analysis?
I don't know yet, because I think at the moment, so definitely, so what I'm interested in is the methodology, in a sense, to get away from that allows you, first of all, to do simultaneous fits of many operators at the same time, and then see what is the interplay between these operators and the standard model parameters, first and foremost the PDFs. So it doesn't matter in a sense to formulate that whether we do SMEFT or HEFT. So once we have a methodology, I think that should be generic enough that we can switch to HEFT. So my dream is that in 2 years from now, I can answer to your questions. So at the moment, I think let's start with SM-EFT because somehow we have more tools also to do the automated computation at NLO of the SMEFT bit of the cross-section, which we don't have for HEFT. So that's the kind of practical reason why we decided to do that.
Sure.
But there is nothing deep or fundamental that prevents us from using HEFT.
I see. Okay. In case we can plan a person-by-person talk in 2 years in Madrid.
Yeah, that would be great. Hopefully this pandemic will be over.
Any other questions? Otherwise, we can thank and clapping again the speaker. Thanks a lot, Maria.
Thank you. It was a pleasure.
And I stop recording.